plays a very important role in the system performance or human performance, and if the physical work environment is not appropriate, then the whole system's performance will be affected. So we will go in detail what kind of component are required in order to have a proper study of physical work environment, and whatever the task you perform, whether it be a social or a physical activity, that physical work environment is necessary. So as far as ergonomic system is concerned, it consists of human, machine and environment. So the system which is consisting of the combination of any these three, so as a ergonomic system. So environment is one of the component in that particular system. So those environment may be related to this lighting system and auditory performance, and as well as there are many other factors that we will discuss. So apart from this physical and social aspects, we will also try to learn about the lighting, noise and our surrounding or climatic conditions. So to start with this lecture, this whole lecture has been divided into three topics. Those are visual environment and lighting, auditory environment and noise, climate control in the work environment. So whether work is physical or cognitive, that role of this environment is important. So any kind of activity is performed in a certain kind of environment. So here firstly we will take visual environment and lighting. So in that visual environment we will learn about the physics of the light, visibility and lighting system. So first we will take the topic visual environment. So this fact we have understood when we started our discussion towards cognitive ergonomics, in which human senses we defined and understood that 80% of the human information input comes from visual stimuli. So the introduction of some of the physical concepts about light as a source of stimulation for the sense of light we will discuss here, and the visual environment, the topics include physics of light, visibility and lighting system. So in this particular section we will understand about the visual environment and work and how the lighting can improve that particular performance. So first we will take physics of light. So what is light? So light we already defined that light is the part of light energy is basically a part of the electromagnetic spectrum. So there are various sort of radiations around us. So the compilation of all the radiations have been given and illustrated with the help of the electromagnetic spectrum chart, in which in fact a human is only capable of visualizing just a limited portion of that electromagnetic spectrum, and those radiations are defined in terms of their wavelength. So around and for our human capacity, only a certain portion of the light having wavelength, a certain portion of electromagnetic spectrum having wavelength of about 400 to 700 nanometer is only visual. That is known as visual light. Other part of the electromagnetic spectrum, which includes microwave, gamma rays, infrared radiations, UV visible UV radiations, X-rays and so on and so forth. So these are the radiations which cannot be detected by normal human eyes, and it requires some of the specific instruments that has been developed and for a particular for a specific radiation there is a specific instrument to so that those rays can be detected. So back to our visual light, since this visual light is only responsible for visualizing our surrounding, so we will focus and we will confine our discussion of visual light throughout our lecture. So here you can see that in fact this particular visual light is within this ultraviolet. If you plot, let's say, electromagnetic spectrum, so it is in between UV and infrared radiation. So here is visible light, and that too is near about 400 to 700 nanometer of wavelength. So this is the range of visible light. So as a definition we can say that the branch of optical physics that is concerned with measurement of light is known as photometry. So here we can in fact we can write here also that the branch of physics, basically branch of optical physics concerned with measurement of light is known as photometry. In fact an instrument that measures this light is known as photometer. So the instrument to measure the light is known as photometer. So now as far as understanding of physics is concerned is okay, but what is its ergonomic interest? So the ergonomic interest in photometry is to provide the proper level of lighting and contrast among objects in a specific workplace where the workers are performing their work. So ergonomic interest, we can say ergonomic interest is in providing proper levels of lighting and contrast in workplace of any industry or in any organization. So in particular this photometer measures the luminous intensity that is emitted by a source of light or reflected from the object surface. The basic quantity in this photometry is luminous flux. This luminous flux is defined as the rate at which light energy is emitted in all directions from a light source. It is the power of light source. Power is a rate quantity and luminous flux is measured in lumens. So a closely related term is this luminous intensity, which can be defined as the luminous flux emitted in a given direction. So specifically luminous intensity is the luminous flux radiated per unit solid angle. We will understand what this solid angle is defined per unit solid angle, and its unit measure is candela, and this one candela is equal to 1 lumen per unit solid angle. So now let's have a clear understanding of what this solid angle and how a particular, this is a point source, how a particular point source of light which is at the center of the sphere, let's say of unit radius, also shown in a solid angle of 1 steradian which intersects the surface of the sphere to create an area of 1 square meter. So now we will understand these terminologies in a clear way. So 1 candela is defined, and there is another unit is a 1 steradian. 1 steradian is equal to the solid angle subtended at the center of the, like this is a sphere, and suppose if we have cut out 1 unit area of on the surface of the sphere, and this particular center is providing some angle, that angle is known as solid angle. So 1 steradian is defined as 1 steradian is defined as the unit of measure of solid angle subtended at the center of a sphere of unit radius by unit area of in fact unit area on its surface. This is illustrated here. In fact it is showing that a point source of light at the center of the sphere and the cone shape of 1 steradian that intersects the surface of sphere to create an area of 1 square meter. So the point source radiates uniformly in all direction and since the total area of the sphere we can define as, how we can define, there is a specific formula for that, that is 4 pi r square, and so the area of a sphere of unit radius, how we can define area of a sphere of unit radius, then r equals to 1, here if we will put, then it will come out as a 4 pi, that is something around 12.56. So thus there are basically 4 pi steradian we can say about the center of the sphere, and analogous to 2 pi radian about the center of a plane circle. So here if a steradian of a unit radius is there, so you can say that there are 4 pi steradians about the center of sphere. So in terms of luminous intensity and luminous flux, 1 candela point source of light radiates of a total of 12.56. So here we can define as the, in fact that those facts can be reduced to one equation, that is F equals to 4 pi I, where F is the light flux and that is basically light flux can be defined as the lumens, and I is the source intensity. This source intensity is defined as the CD, that is candela. So now in practice there is no as such anisotropic point source of light. So luminous flux radiates from a real light source with different intensities in different directions. So using a photometer, basically, so if we take, let's say, a photometer, so light measurements can be taken. So let's say using a photometer, light measurements can be taken from a particular direction relative to source to determine the luminous flux emanating in that direction. So the amount of light shining on a surface is can be referred as a illuminance. So now, so illuminance can be defined as the luminous flux shining per unit area on a surface. Unit can be as an lux, Lux, and in a short form you can write as an Lx. So 1 lumen per square meter it is defined as, and then another term that is defined in the describing light, that is luminance. So this luminance is defined as the amount of light reflected from a surface. So here that particular unit is candela per square meter, and it depends on the illuminance, that is amount of light striking the surface. Reflectance, it depends on the color and texture of the surface. So in equation form, if you want to write, that is E equals to F by A. You please note down this formula, because these formulas are somewhat necessary in order to predict the exact value that is required whenever we define any workplace environment in terms of its visual abilities. So E equals to F by A, where E is the illuminance, that is expressed in lux, and F is the luminous flux, that can be defined as lumen, and A is the area of illuminated surface, that can be defined as the meter square. So this illuminance decreases as the distance from the light source increases. So that the reduction is proportional to the square of the distance as expressed in this written equation. So where E is the illuminance is defined, and I is the luminous intensity. Of any light source, that can be expressed in the candela CD. So D can be defined as distance of let's say surface from source, that is expressed in meter. So this equation assumes that the surface is perpendicular to the line of distance between source and surface. That we will clear in the next slide. So here you can see that we assume that this particular surface and the light is falling perpendicular to the surface, making 90 degree. So for those reasons, that formula is coming out as an E equals to I by d square. So this figure is giving you the angle of incidence defined for particular equation, this equation, and since always it is measured from the perpendicular, so from this line of direction, so theta is defined with the perpendicular line of the distance from the source and surface. So since another line I can add here so that the understanding could be more clear. Suppose this is the source and this is the light source in fact, and light is incident on this surface, and let's say if this particular light is is giving some angle to the falling light, so this particular angle, and it is reflected from this to this, so this particular theta is the some angle. So here is the surface. So you can find the difference between this A and B. So this is the light source. So if the angle of incidence, and that is this, is other than the perpendicular, so illuminance must take the angle of incidence into the account, and it can be determined as E equals to I by d square into cos theta. So for this case this formula is applicable, and for this particular case when angle of incidence is other than normal, then you will use the formula, that is E equals to I by d square times cos theta. So where theta is the angle of incidence, and note that when if you can see this particular equation, where if you will put theta equals to 0, then cos theta will be 1, and this particular equation will be reduced to equals to I by d square into 1. That equation and this equation are 1 equals to 2. So the angle of incidence should be in the direction of the normal that has been put from the surface. So this particular incident light at some sort of angle, let's say theta, so that we have described. And now the another aspect that we need to understand, that when light shines on a surface, some of the light is absorbed into the surface where light is particularly incident, and light is absorbed here, and some of it is reflected from the surface. So in addition, for material that are translucent, some of the light is transmitted through the material. The light that is reflected from an object is what allows human to visually perceive it. So the amount of light reflected from the surface is luminance, and its unit of measure is that we have understood in this particular. So luminance is defined as the amount of light reflected from the surface, and its unit of measure is candela per square meter, and this particular luminance of a surface depends not only on the amount of light striking surface, or amount of light shining on it, and also on the color and texture of the surface. So the proportion of the light reflected from the surface to the light striking it is the property of the surface known as reflectance. So we have also to define this reflectance. So reflectance is also necessary to be understood, and that is defined in the SI system of unit as follows, that R equals to pi L upon E, or capital L equals to RE upon pi. So where R is the reflectance, this is the dimensionless fraction, and L is the luminance that is expressed in candela per square meter, and capital E is illuminance that is expressed in lux, and the pi term in the numerator is the conversion factor to account for the difference in the units between the units of luminance and illuminance. So basically there are some values for various objects and paint colors, so that is defined. So that's all for in fact we can also solve one numerical based on that. So we will try to solve one numerical, then we will close this lecture. So let's have a one example or one question based on the light from isotropic source. So let's say one isotropic source, it has an intensity of one isotropic light source has an intensity of 50 candela, and the source is located, let's say 3 meter away. This particular light source is away from a wall that has a reflectance of 0.65. So calculate, the first is total luminance flux emanating from its light source, B, you have to calculate the illuminance of the wall, and also you have to calculate the luminance emitted by the reflected light. So these things, since the theory of these three aspects we have discussed in the previous slide, so it will be very easy for you to solve this particular problem. So try to solve it. I am giving you some time to solve it, and you try it at your own end, and then I am giving you the solution of that, so that a complete understanding of the topic discussed is could be developed. So the solution I am discussing here, so the total luminous flux emanating from the light source can be defined as the F is equal to 4 pi I. So you have the value of I as an 50 candela. So you can put here as 4 pi times 50 candela, whatever will be coming as an lumen. The B that you need to find is illuminance of the wall. That can be find out as E equals to I upon D square. That is 50 upon, it is, since light source is located 3 meter away, so distance is 3. So in this way you can find out the number that can be expressed in the lux, and the C is the reflected light that can be determined by this equation, that is basically R equals to pi L upon E. Since we have to calculate L, so E R upon pi, that can be defined as the, so the value that will be coming as if F is equal to 4 pi I will be, if you multiply these factors, so 628. Here what it will come out as a E is 5.55. so the 5.55 value will be putting here. So in this way the 5.55 into 0.65 upon pi, which will give you the value that will be expressed in candela per meter square. So that is this is a very simple question that anyone can solve if you are in above 12th level standard qualification. So this can be solved based on the simple formula putting. The things are given in the question itself, you need to recall these formulas and put the values and get the answers. So it will be something around 1.15 candela per meter square. So I am closing this lecture. So just a fact which I used to add in maximum slides possible. So did you know that a 23-year-old Google employee lives in a truck in the company's parking lot? When 23-year-old Brandon started working as software engineer in Google, he opted out of settling into an overpriced San Francisco apartment. Instead, he moved into a 128 square foot truck. Since we have started a very fresh lecture of physical work environment, so now it's time to cultivate your thinking. So in that series I am giving you one task. If you are a project manager at Maruti Suzuki, let's say, and how would you take care of the environment to make it look more productive and effective? So think about that perspective, and that's the graffiti for you. Enjoy it. That's all for now. Thank you.